So let's take a look at these two questions that are here in the notes. All right, got a couple of students. They're going to go on a little sightseeing tour. They're going to be leaving from the school and heading down to Battleship Cove and Fall River. All right, and if you've been there before, you know that you drop down Route 24 when turns into Route 79, and it brings you right down to the cove, and you can see the ships right there for their sightseeing and visiting. Okay, and two students are going to take two different manners to get there. Okay, first student's going to drive. That's question number 2. All right, so we're going to leave from the high school, hop onto Route 24, and drive down the roads all the way to the cove. Okay, now if that student wanted to figure out how far the distance was, no phones, all right, cell service is out, Google Maps can't help. How could that student determine how far the distance is from the school to the cove? Yeah, you look at your odometer, okay, which is the numbers that keep twirling at the bottom of your, usually at the bottom of your speedometer in a car, all right? And if you take a look at the odometer, specifically, we're interested in the odometer's value at the end of the trip, all right? Because we're going to subtract that from the odometer's value at the start of the trip. Okay, so for example, let's say that your car has 50,000 miles on it when you leave. So if you have 50,000 miles when you left, and then you arrive and you see that it's 50,027 miles, then we know that the distance between the two is 27 miles. We just do the value of the odometer at the end minus the value of the odometer at the beginning, all right? Now, the value of the odometer at the end, that's another way of saying the position of the car. So we want the position of the car at the end of the trip, okay, which is 50,027 miles, minus the position of the car at the start of the trip. Okay, all right, and we know that position function is S. So we have S of the end. Let's call the ending value B, all right? So S of B minus the position at the start, all right? And you can kind of see maybe where we're going with this, all right? So T starts at time T equals A, and we get down there at time T equals B. The position at the end, S of B, the position at the start, S of A. S of B minus S of A, where S stands for the position function, that represents the total distance which the car traveled, okay? That's question number 1. Now let's look at question number 2. This is our second student. Second student's not going to drive, right? Second student's moving in style. She's flying, all right? So she hops into the international airport right next door to the school, takes off and flies down to the cove. It's going to land on the brand new aircraft carrier that's not there yet, all right? But when that student gets down there, she's not quite sure where she's going. So what she's going to do, she's going to follow the exact same track that the driver, right? Because students both know that Route 24 and 79 lead us right to the cove. So she takes off, sees Route 24, and shoots down Route 79, and she lands on that aircraft carrier. She travels the exact same distance, okay, as our other person, okay? However, she can't calculate her distance traveled in this manner, right? Because as we talked about with previous problems, right, there's no odometer in a plane, right? There's an odometer in a car, but there's no odometer in a plane. The odometer in the car is connected to the tires. Remember how many times the tires go around, every certain number of revolutions equals 1 mile or 1/10 of a mile, and it triggers the next number, okay? We don't have that in the plane, all right? But we already determined how to figure out how to calculate distance traveled using an airplane. What did we do? All right, it wasn't position, it was velocity. It was the integral from A to B of our velocity function. Okay, that right there, remember I think it was example like 3 when we were talking about Riemann sums, okay, or distance traveled. That will tell us how far an object travels, okay? Even if we don't use the plane, go with the runner. Remember the marathoner? All right, when she was running, we looked at her velocity from a particular A value to a particular B value, and that told us that she had run 18 miles. This right here is a way to calculate our distance if we don't have the position function. If we have the position function, we can calculate the distance doing the s of b minus s of a. If we don't, then we can use the definite integral from a to b of our velocity function. But while this measures the distance the plane traveled, and this measures the distance which the car traveled, both objects traveled the same distance, which means that these two expressions are equal to each other. And that's huge for us. And here's why. Because what's the connection between velocity and position in general? What did we learn way back at the beginning of the year? Exactly. Velocity is the derivative of position. So what we can do here is we can rewrite this. This is the integral from a to b of the derivative of position, dt. And that's equal to s of b minus s of a. Okay, so if we have the derivative and we're taking the integral of that, well, they're wiping each other out, and we can actually calculate what's going on by just looking at the original function. Okay, now it seems kind of weird because we're dealing with position and velocity. Let's generalize this, okay? It doesn't matter that it's position, velocity. This can be a function for anything, okay? So let's go back to our old faithful of f. So we got the integral from a to b, and this is going to be f prime of x. Instead of s prime of t, let's just go with what we're used to. All right, changing the s to f, we're keeping the prime, and then changing the independent variable from time to x, because it doesn't matter. All right, so we have f prime of x dx. Right, and that's equal to, again, s is f, so this is f of b minus f of a. Okay, now this right here, that is known as our fundamental theorem of calculus, and it's a huge part of the course. But we're going to pause it for a second because we have to talk more about how we get to this idea of the fundamental theorem of calculus and the mini step in between. Okay, so just keep those words in mind, fundamental theorem of calculus, but check out what's happening here. What we're saying here is this right here, the integral of the derivative, they wipe each other out. Notice, integral and derivative. They're both right here, okay? Integral and derivative. Neither is right there. That means that they've wiped each other out, like addition and subtraction, or multiplication and division, or e to the x and the natural log of x. They are inverse operations. Okay, so this idea of the integral, it's the reverse of the derivative. It's the inverse of the derivative. It's the opposite of the derivative. Okay, that's why we're dealing with what's known as the fundamental theorem of calculus. This is connecting everything we've done in the first half of the course to everything we're about to do in the second half of the course. Okay, now, more importantly, what it tells us is if we're given the derivative, then all we got to do is we got to plug a and b in, but not into the derivative, into the original function, which means we have to get from the derivative to the original function so that we can plug those numbers in. Okay, well, if we're not doing the derivative, we're doing the opposite of that. That means we need to get the antiderivative. And that's our next topic, antiderivatives. Okay, how do we go from the derivative back to the original function? We're going to do the reverse of what we've been doing in the first part of the course.